Hello, my dear students. I welcome you once again to this current lecture. As we know that we are discussing from the last lecture the different methods for the determination of the transport number of the ions. So we already completed the first method for this determination, that is called as the Hitop's method. Now in a current lecture we are going to take the next method for the determination of this particular transport number. That method is called as the moving boundary method. Now as far as this second method is considered, we know very well that in a last method we know the basis of this particular Hitop's method. In that method we take into consideration the changes in terms of the concentration of this electrolytic solution in the vicinity of the particular electrodes. But now as far as this second method is considered, that is a moving boundary method. In this method, what we have to take into consideration? So this method is based upon the motion of ions. We have to take into consideration the motion of ions. This motion of ions observed directly. This motion of ions observed directly under the influence of under the influence of under the influence of applied potential, under the influence of applied potential instead 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 of concentration change instead of concentration change at the electrodes, instead of concentration change at the electrodes. So this is the basis of this method. Means as far as this moving boundary method is considered, this method, what we have to consider here? So this method is based upon the motion of ions. So we have to consider the motion or the movement of ions directly under the influence of applied potential. We have to apply the potential, and under this applied potential what type of motion of ions is observed, or what is the movement of ions to be observed directly. So that we have to take into consideration instead of the concentration changes at the electrodes. Means in the last method we consider the changes in concentration at the electrodes, in the vicinity of electrodes. Instead in this method we have to take into consideration the actual movement of the ions. So this is the basis of this particular method of moving boundary method. Now this method consists of the important experimental setup. So as far as this method is considered, this type of experimental setup is there. This method consists of this type of the sophisticated setup. Now what is present in this experimental setup of this method? So as far as this experimental setup of moving boundary method is considered, this consists of a cell. It consists of, or this cell consists of a graduated tube. This is called as one graduated tube. It is mounted vertically. It is present vertically. So it has the two electrodes. This graduated tube has the two electrodes. These two electrodes are fixed at the two ends of this tube. This is the upper end of this tube and this is the lower end of this tube. So at the upper end of the tube we have to take the electrode as a platinum, and at the bottom side we have to take the electrode as a anode. In this particular cell we have to take a particular solutions. Now in these cells we have to take the two different type of the electrolytic solution. First electrolytic solution is called as the MA. This is the first electrolytic solution, MA. The second electrolytic solution we have to take here, that is called as the M-A. It is a M-A. What is the similarity in this particular electrolytic solution? In this both these electrolytic solution, anion is a common. In this case also anion is a, in this case also anion is a, just we change the cation. In this case cation is a M, while in this case the cation is a M dash. So we have to take such a type of the two electrolytic solution in which the anion is a common. Now after that, in the upper part or in a upper end of this tube, a platinum wire is immersed. A platinum wire is immersed from this upper end of the tube. Then that platinum wire is to be treated as the cathode. This platinum wire is to be treated as a cathode electrode, while at the downward side end of this tube or at the bottom end of this tube, a cadmium metal is sealed. A sealed cadmium metal is there. Then that cadmium metal acts as the anode. So the both part or the both ends of this tube has the two different type of the electrodes. The upper end made up from the platinum acts as a cathode, while the bottom end is made up from this cadmium and acts as the anode. Now we take here the two different electrolytic solution having common anion. Now while taking these two particular electrolytic solution, we have to take into consideration that whenever we take the two different type of this electrolytic solution, they must have a sharp boundary between them. They must have the sharp boundary between them, means we can easily identify the two different type of the electrolytic solution. Now this maintaining this sharp boundary between this type of the solutions is based upon we may take the two different type of the electrolytic solution having different refractive indices, having different refractive indices, having different refractive indices. So on that basis we may make a sharp boundary between these two type of the electrolytic solution, or we may take the such a type of the solution which have the different colors, which have the different colors, So for maintaining a sharp boundary between these two electrolytic solution, we have to either take the different refractive indices of a solution, or we have to take the different colored electrolytic solution, by using which we can make a sharp boundary between these two type of the electrolytic solution. Now as far as this sharp boundary between this type of the electrolytic solution is to be concerned, it is not a simple job, because we have to take a special precautions while considering this type of the boundary between this type of the two electrolytic solution. So for this purpose we may take at some time we may take the different type of the density of the solutions. The high dense solution can be placed at the bottom side and the less dense solution can be taken at the upper part. So by using that also we can make this type of the boundary between these two type of the electrolytic solution. Now as far as the working of this particular instrument to consider, before that we must know the remaining parts present in this particular solution. Just we completed the first important part, that is a graduated tube. Now to this graduated tube a colorimeter is arranged, a colorimeter C is arranged or connected to this particular battery, this particular tube. After that a millimeter is joined to this particular graduated tube. Then the variable resistance is there, power pack is there. So this is a simple instrumentation for this moving boundary method is there. Now as far as the working of this particular method is considered, so what happens whenever a current is passed, now we have to pass the current from this external battery, we have to pass the current through this tube, or this current is passed from this external circuit through this cell. Then what happens, the boundary between these two type of the electrolytic solutions, this boundary between the two electrolytic solutions get shifted or get changed, or the shift in this boundary can be takes place in upward direction, in a upward direction. That is, this boundary can be changes from this a dash towards this b dash. So this type of change or shift in this boundary can be takes place from this a dash toward this b dash. So during this type of the change in this boundary or this movement of the boundary from a dash to b dash, we have to take into consideration the volume swept. We have to take into consideration volume swept. So what type of volume shift can be observed during such a type of the boundary change, so that we have to take into consideration. Then by observing this type of the volume shift, we can get an idea regarding the particular movement of the ions. Now, the what type of quantity of electricity can be passed? What type of quantity of electricity can be passed through this cell? What is the quantity of electricity can be passed through this cell is determined by the deposition of silver, in kilometer C. The deposition of silver can takes place in this kilometer C, and by taking into consideration this deposition of silver, we can calculate the quantity of electricity that has to be passed through this cell. Now, by taking into consideration these different aspects, means first of all we have to take into consideration this volume shift, means whenever a movement of this boundary from A dash to B dash can be takes place. So what is the volume shift is there, so that we have to take into consideration. After that, we have to estimate the quantity of electricity, or the electricity that has to be passed through this cell is determined with the help of deposition of silver in kilometer C. So these two parameters we have to take into consideration for determining the transport number of the ions. So this is a simple working of this particular moving boundary method. Just when we pass this current from this external battery to this cell, then what happens? There is a movement of the boundary takes place in upward direction, that is from A dash to B dash, during which a volume shift is there. Then we have to take into consideration this volume shift. At the same time, what is the amount of the current, sorry, the electricity can be carried out by this particular ions. So that has to be determined with the help of deposition of silver in kilometer C, and by using that we may determine now the transport number of these particular cations and particular anions. Now, in order to determine this particular transport number of cations and anions, so we have to take into consideration, we just know here, so we have to take here into consideration calculations. So what type of calculations we have to carry out for considering or for determining transport number? So first of all, we have to take into consideration some simple parameters. First we have to consider here V. So what in by this V is there? So this V is nothing but the volume shift. This V is the volume shift. So how this volume shift can be takes place? So it is to be shaped by the moving boundary. Volume shift is there by moving boundary, from A dash to B dash, from A dash to B dash. So during such a type of the movement, volume shift is there, that is to be taking as a V. After that, we have to take into consideration the quantity of electricity. This Q is there, that Q is called as the quantity of electricity. This is quantity of electricity measured in kilometer, measured in kilometer C, measured in kilometer C. So this is the second parameter we have to take into consideration. After that, a capital C is there, this capital C. So this capital C is a concentration of cations. This is a concentration of cations in equivalents per liter, in equivalents per liter. So this type of the simple parameters we have to take into consideration for the calculations. So by using this particular parameters, we have to calculate first the transport number of cations. So the transport number of cations, is nothing but the T plus. So this T plus is equal to V into C divided by 1000 into Q. So this is the first equation which is useful for calculating this particular transport number of the cations, that is equal to V into C divided by 1000 into Q. In this case we know very well whatever this is V is called as a volume shift by moving boundary. This C is called as the concentration of cations. This Q stands for quantity of electricity measured in kilometer C. So this is a equation to calculate transport number of cations. From this we may calculate now transport number of anions. Now we may calculate here transport number of anions, that is to be equal to T minus, we know very well that we have to take here 1 minus transport number of cation. So it is to be equal to T minus is equal to now 1 minus V into C divided by 1000 into Q. So this is the equation useful for determining the transport number of the particular anions. So this is a simple calculation from this moving boundary method for the calculation of the transport number of cations and anions is there. Now as far as the magnitude of this particular transport number of ions is considered, it is to be observed that this is unaffected by applied current strength. These transport numbers are unaffected due to the applied current strength, but they get somewhat change, or somewhat change can be takes place as far as variation in a concentration of solution can be takes place. If we change the concentration of solution, at that time there is maybe a change in transport number can be takes place, but that transport number cannot be get affected by the applied current strength. So this is a second important method for the determination of the particular transport number of cations and anions, called as the moving boundary method. So this method is based upon the actual movement of ions directly under the influence of the applied potential. So for this method we just studied here a simple experimental setup. So this simple experimental setup is there. By using this experimental setup we can study, or we can determine the transport number of the particular ions. So this is the second important method for determination of the transport number of the ions. So with this I'll stop here in this current lecture. Remaining points we will take in a next lecture. So thank you so much.